All right, good morning. Today is Friday. Talking about my day, I'm going to be heading over to the FCAT Center. Um, it turns out that this guy is actually a ride. It's called Spaceship Earth. It's a ride that looks at the past and the future, and it's pretty nice. It's fun. But since this is a math class, the actual term here is a Pentacus dodecahedron, I'll be doing this today. I'll let you know how it goes. It's actually a ride that goes inside this geodesic dome. But let's talk more about what you're going to be doing today. What you're going to be doing today is you're going to be solving polynomial functions. Method one, we could solve these things by factoring. This is a technique that we've done for a while. Here's the first example. All right, so to solve this sucker, we first have to find the roots. Another term for roots is zeros. The zeros are also known as the x-intercepts, which are the values that make the f of x 0. So we're going to get 0 equals x to the fourth minus 10x squared plus 9. This is a factorable quadratic in disguise. There are numbers that multiply to 9 that add to negative 10. That's 9 and 1. It's negative 9 and 1. And then we'll have x squared minus 1 and x squared minus 9. Both of these can be factored further with the difference in difference of squares. And what we have here are 4 linear factors that I can now set equal to 0. So solving this polynomial equation, I can write x minus 3 could be 0. I can have x plus 3 equal to 0, x minus 1 equal to 0, and then x plus 1 is also 0. It's nothing more than the zero product property, which says that if things multiply to equal 0, then each factor could be 0. So my solutions here are 3 and negative 3, 1 and negative 1. And so go ahead and verify with your graphing calculator that if you were to graph this function, you would have x-intercepts at 3, negative 3, 1, and negative 1. Your end behavior is looking like this. You have an even power with a positive leading coefficient. But that's an example of factoring. The main purpose of today is solve these polynomials that cannot be factored. Here's a great example. This is a 5th power degree polynomial that we have to find the solutions for. Now, one thing we're going to recognize here is let's use something called the fundamental theorem of algebra. And I wrote it as big as I can here to help us out. Boy, here it is. And this is a very layman's way to say this. It's a little more complicated, but given a polynomial, the degree equals the number of complex zeros. So if I had to make this even more simple, let's see, a polynomial, the degree equals the number of zeros. So what we're saying here is if I go back to this example, I know that there are 5 zeros in this particular function, meaning 5 values of x that make this thing 0. Now, not necessarily x-intercepts because we can't have imaginary solutions, but there could be 5 x-intercepts, but not more than that. So one thing we can do here is play a game called Capture the Zero. Find the values of x that make this thing equal to 0. One way we can start this is by giving us a starting point. It says, give the polynomial function and the 0 of f, find the other zeros. So I know that negative 2 was a 0. Another way of saying that is f of negative 2 does equal 0, which is an x-intercept. So if I know that negative 2 was a 0, that tells me that x plus 2 is a factor. All right, which tells me if I take p of x, f of x in this case, and divide it by x plus 2, I should get a remainder of 0. Let's do that. Let's use synthetic division. Let's put a negative 2 on the outside, and let's divide that by 5, negative 1, negative 18, and 8. So let's see, we did this yesterday. We're going to bring down the 5. We're going to multiply to get negative 10. We're going to add to get negative 11. We're going to multiply to get 22. We're going to add to get 4, multiply to get negative 8. And look at that. My prediction was true. 0 is the remainder, which implies that negative 2 is a 0, which tells us that x plus 2 is a factor of this polynomial. So what that means is the remaining quadratic, 5x squared minus 11x plus 4, is also a factor. So if I find the zeros of this remaining quadratic, I have found the zeros for our original polynomial. So to find the zeros, 5x squared minus 11x plus 4, I can do this lots of ways. I can look for a factor, I can use the quadratic formula. Let's check for factorability. 5 times 4 is 20. Are there factors of 20 that add to negative 11? I don't think so. So what we're going to have to do here is we're going to have to use the quadratic formula. So let's start that process. All right, see with me. X equals negative 11, positive 11 plus or minus the square root of negative 11 squared minus 4 times 5 times 4 all over 2 times 5. Oh, okay, so let's rewrite this out. It's be 11 plus or minus the square root of 41, and we'll divide that by 10. Let's get some decimal approximations. Okay, here they are. If you get the decimal approximations, we get 1.7 and 0.46. So these are the 3 zeros. So let's cap up what we know. The zeros of this polynomial are the one that was given to me, the 2. I also have 1.7 approximately and 0.46. They could ask for either the exact answer, which is the square root here, or they could ask for the approximation. And it helps to get that approximation because what we can do now is we can actually graph this. We know the end behavior. We know where it crosses the x-axis. So let's see. That end behavior is an odd degree with a positive leading coefficient. So it looks something like this. And then we're going to have the x-intercepts at 2, negative 2 is the x-intercept, and then 0.46. So we're going to have to look something like that. So let's do that. Let's verify that this is the graph or something like it in your graphing calculator. Go ahead and type that in, and then press graph and see if that's kind of the graph that we get with the appropriate x-intercepts and behavior. All right, here's another good example. Sometimes they will tell us the factor, and with that we can find the other zeros. So let's see, if x plus 2 is a factor, that means f of negative 2 equals 0. That means that when I replace x with negative 2, it makes the y value 0, which is in turn a 0. So that means that negative 2 is a 0. In this case, x-intercept. So to find the other zeros, we have to do some division. So negative 2 is going to go outside here with the leading coefficient of 3, negative 4, negative 28, and negative 16. Before you start this process, let's remind yourself that the remainder will be 0. I know that. If I don't get a remainder of 0, then I did something wrong. All right, let's try that. So bring down the 3 and get negative 6 for the multiplication. Add to get negative 10. Multiply to get 20, add to get negative 8, multiply to get 16. And look, it does add to 0. So the remaining quadratic that is a factor is 3x squared minus 10x minus 8. All right, so look at the instructions. The instructions say to completely factor this f of x. Well, all I have left then is to factor this quadratic. Let's use the AC method. 3 times negative 8 is negative 24. Factors of negative 24 that add to negative 10. I believe that's going to be negative 12 and 2. So let's rewrite this as 4 terms. And then, taking out a 3x, taking out a negative 2, we want to take a positive 2 out, so that we'll get the minus 4 here. So then our factor will be, let's see, x minus 4 is what the common factor is, and then a 3x plus 2. So if I multiply that by my original factor, which is x plus 2, let's see, I'll just tack it on in the end. So that is the complete factorization of f of x. And what they could do is they could ask for the zeros, but they don't. Well, let's assume they did. So the zeros of this, or the x-intercepts, will be a 4, negative 2/3, and then negative 2. So in the graphing calculator, if you graph this function, you will find x-intercepts at 4, negative 2/3, and negative 2. Okay, so here's the third example. Notice on the previous two examples, they gave us a starting point. They said x plus 2 is a factor, which negative 2 is a 0. On the first example, they said, hey, negative 2 is a 0, find the other zeros. So we're going to become dependent upon the graphing calculator. Because notice here, remember that fundamental theorem that I mentioned a few minutes ago? It was big and bold. Hopefully you wrote it down. I'll show it to you again. Right, ooh, yes, here I am, right here. Given a polynomial, the degree, the highest power is the number of zeros, complex zeros more precisely. So I know before I even start this problem that I'm looking for 3 zeros. There are 3 zeros to this guy. And we're only concerned about the rational ones right now. So what we might do is graph this in our calculator, and I've done that for you here. Here it is. So let's take a look. I'm going to look at this graph and recognize zeros at negative 2 and a 0 at 1. We might remind ourselves that the multiplicity of that 0 is going to be 2. So this graph tells us the zeros. The zeros are, let's see, negative 2 and then 1 with and we would say a multiplicity of 2. So there are the 3 zeros. Negative 2 occurs once, and then 1 occurs twice. So one thing we could do is verify that with our synthetic division. So let's start with negative 2. Let's do negative 2, and we're going to divide that by our polynomial. So 1x to the third, 0x squared, negative 3 and 2. So we're going to bring down the 1. Multiply to get negative 2 and add to get negative 2. Multiply to get 4, add to get 1. And multiply to get negative 2. And look, they do add to 0, which tells me that x squared minus 2x plus 1 is also a factor of p of x. But this is factorable. It's just going to be x minus 1 times x minus 1, which gives you the other 2 zeros, which are 1 and 1. And notice it doesn't matter with which 0 I started with. Let's start with one of the 1s and see what happens. So let's see, I'm going to put a 1 inside the box. And I'm going to put the 1, 0, negative 3, and 2. Bring down the 1. 1 times 1 is 1, add to get 1. Add to get 2, negative 2. And look at this, the 0 is the remainder. So the other zeros are x squared, come from x squared plus x minus 2. That does factor. That factors into x minus 2 and then x plus 1, which are the zeros of 2 and negative 1. That is, let me fix the signs here. This is a plus 2, that's a minus 1. So the zeros are negative 2 and 1. And so we've done this several ways. We looked at the graph. And from the graph, we saw where the x-intercepts were, which are the zeros. We also used synthetic division to find zeros to verify that's the case. Let's do this example. Find all the zeros. So notice they do not give us a starting point. They don't say negative 5 is a 0. They don't say x plus 5 is a 0. So we're going to use our graphing calculator. So get your graphing calculator. Plug this in and see what you find. All right, I just did that, and hopefully you did as well. But I'm looking on the standard screen something like this. All right, so it looks like we only have one x-intercept, and that x-intercept appears to be 3. All right. Now the total number of zeros we're looking for is 3. All right, so we're looking for 3 zeros. which tells me that two of these zeros are probably imaginary, but one of them is real because those are the x-intercepts. So let's see, 3 is a 0. So let's use our synthetic division. We're going to go 1, -3, 4, -12. And let's remind ourselves that we will get a remainder of 0 if everything works out. So we're going to bring down the 1, multiply and get the 0. Then we're going to multiply and get 0 and add to get 4. So our remaining quadratic is x squared minus 4 equals 0. Plus 4. And so solving this quadratic requires the square root property. We get x squared is -4. And so x is positive -2i. So there they are. That imaginary 0 of 2i, -2i does not show up graphically. They do not cross the x-intercepts when you have this is the complex. So in this case, we would say there's 3 complex zeros. So there's one real, which is found on the x-intercept. That's a 3. And there's 2 imaginary. The imaginary solutions are 2i and -2i.